Module 5, Lecture B, Capstone Automation. By the end of this lecture, you will be able to design a complete Python script for an applied chemical engineering task, integrate functions, data structures, loops, and file output into one workflow, and evaluate project code for correctness, readability, and engineering usefulness. Project design. Problem definition. Begin a capstone automation project by clearly defining the engineering problem the script will solve. Focus on the practical purpose, what decision or task it supports, who will use the results, and why automation is needed. In chemical engineering, this might involve automating material balance estimates or reactor performance summaries. Avoid vague goals and instead state how the script will process data, calculate useful indicators, and help engineers make decisions. For a capstone automation project, define a clear, manageable scope. A good Python script should take specific input data, apply the needed engineering logic, and produce understandable results. Rather than automating an entire plant or lab, focus on one workflow and clearly state what the project includes and excludes. This keeps the work focused and ensures it addresses the intended problem effectively. When defining an engineering automation problem, emphasize its practical value, not just the computation. A good script should improve repeatability, accuracy, and speed, especially when results must be updated or checked quickly. Whether used for lab data processing or design scenario testing, the goal is to reduce manual effort and errors. Clearly explain the real-world need and why mistakes matter, so the work is framed as a useful engineering tool rather than simply a coding exercise. Python code problem definition. Before writing code, clearly define the automation problem and make sure the script serves a real engineering purpose. Keep the project narrow enough to test and verify effectively. A list is created to store candidate capstone projects, with each project represented by a dictionary of key details. The first entry describes a batch reactor run summary project, including its title and purpose, summarizing conversion and temperature targets. This structure keeps project information organized so it can be evaluated and compared later. The project is aimed at process development engineers and uses time, temperature, and conversion data as its key inputs. Its main outputs are a target flag and a summary report, which help engineers understand and act on the automation results. The project scope is defined by what is included, what is excluded, and why automation matters. It includes monitoring performance indicators and flagging unusual runs, while excluding kinetic model fitting and scale-up design to keep the work focused. Automation adds value by improving repeatability, speed, and consistency. This code defines a project for checking heat exchanger duty by comparing measured heat duty with expected values. It is intended for plant support engineers and uses key inputs such as flow rate, temperatures, and heat capacity. Together, these details define a focused engineering tool for evaluating heat exchanger performance. The project defines its expected outputs, including a duty comparison and a warning message, and clarifies its scope. It includes items such as a sensible heat balance and percent deviation, while excluding tasks like fouling prediction and mechanical design. Automating the work is valuable because it improves accuracy, traceability, and consistency. The function scores how complete a project definition is by checking a few key criteria. It starts at 0, then adds points when the project has a clear purpose, defined users, and at least 2 inputs. The final score gives a simple measure of how well the project has been specified. The code raises a project score when key parts of the project are filled in. It checks that there is at least one output, one included item, one excluded item, and at least two automation values. Together, these conditions help measure whether the project is sufficiently well defined. The function returns a score showing how well a project definition meets the checklist criteria. This helps the rest of the script judge and compare project definitions based on their readiness and completeness. The readiness label function compares a project score with its maximum possible score. If they match, it returns the label well-defined, turning the numeric score into a simple description of the project definition's completeness. The code checks whether the score is within 2 points of the maximum. If so, it labels the project as needing only small edits, meaning it is nearly complete but still requires minor adjustments. The function returns needs redesign when a project definition scores below the required threshold. This means the project is not yet well defined and needs significant changes before it is ready for further development. The evaluation begins by setting the highest possible project definition score to 7, based on the checklist criteria. An empty results list is then prepared to store each project's evaluation outcome, including its name, score, and readiness label. Each project is reviewed by calculating a definition score, which measures how well the project is specified. That score is then compared with the maximum possible score to assign a readiness label, such as well-defined, needing small edits, or needing redesign. The code records each project's evaluation by adding its name, score, and readiness label to the results. This creates a concise summary of how well the project meets the predefined criteria. The code prints a header for the Capstone problem definition checklist. This introduces the project evaluation summary and clearly signals that the following results relate to the project scoring process. The code goes through each project result and prints a clear summary with the project name, its score out of the maximum, and its readiness label. This makes the evaluations easy to review and compare. The process selects the most implementation-ready project by using the max function with a scoring rule to find the highest rated option. It then creates a concise summary that names the chosen project and explains how it helps its intended users achieve their goals. The project purpose is converted to lowercase for consistent output before the statement is printed or reused. The code displays a short message identifying the selected project. It explains that the project was chosen based on its score and summarizes how it helps the intended users achieve their goal. The print function sends this summary to the console. This script compares two engineering project ideas using a checklist that scores how clearly each one defines its purpose, users, inputs, outputs, and automation value. It assigns each project a readiness label, summarizes the results, and then chooses the highest scoring option as the most promising project, noting its purpose and target users. Input requirements. Before building a chemical engineering script, clearly define the required inputs, such as flow rates, temperatures, and pressures. Knowing what data is needed and why helps ensure the calculations are meaningful. For example, estimating heat exchanger cooling duty requires information about both streams. Clear input definitions reduce ambiguity and connect the engineering problem to the computation. When setting input requirements for a chemical engineering script, clearly define each data point's format, units, valid range, and source. The script should account for manual or file-based entry, check for missing or invalid values, and convert units consistently when needed. This helps keep results reliable and prevents small data entry mistakes from causing errors. Effective input planning makes scripts easier to use, maintain, and expand. Organizing inputs clearly helps engineers understand what information is needed, supports stronger validation, and makes scripts more adaptable across projects. A well-designed script should not only perform calculations, but also guide users toward accurate data and reliable engineering results. Python code input requirements. Clear project inputs are essential for reliable engineering calculations. Validation helps prevent misleading results in chemical process work, while organized requirements make scripts easier to maintain and extend. Define a required inputs dictionary to describe the parameters needed for the engineering calculations. Each entry identifies an input, its unit, and its acceptable minimum and maximum values. This lets incoming data be checked consistently, helping keep the calculations accurate and reliable. The Input Requirements Dictionary is expanded with two new engineering calculation fields: outlet temperature, measured in degrees Celsius with a valid range from 0 to 120, and density, measured in kilograms per liter with a valid range from 0.5 to 1.5. These added limits help support accurate input validation and later calculations. The required input settings are being updated to include heat capacity. Its unit is kilojoules per kilogram per degree Celsius, and accepted values must fall between 1 and 6. This range helps keep the engineering calculations valid and accurate. A design case dictionary stores the key inputs for a small design scenario. It records a flow rate of 85 liters per minute, an inlet temperature of 92 degrees Celsius, and an outlet temperature of 35 degrees Celsius. Keeping these values together makes them easy to reference in later calculations or checks. The design case is updated with two key fluid properties: density and heat capacity. The density is set to 1 kilogram per liter, so volumetric flow can be converted to mass flow. The heat capacity is set to 4.18 kilojoules per kilogram per degree Celsius, which is needed to calculate the cooling duty. The function starts by creating a place to collect validation messages. It then checks which required inputs are missing by comparing the required items with the values that were provided, and sorts the missing items for consistent reporting. This helps ensure that any absent data is identified before later calculations continue. This code checks each missing input and adds a message noting what was not provided. This makes it clear which required data is absent, so the user can correct the issue before calculations continue. The process checks each requirement against the available values and only continues when a matching value exists. If a required key is missing, it skips that item and moves to the next one. This keeps validation focused on available inputs and avoids errors from missing data. The code gets the current input value for the given key, then checks whether it falls between the required minimum and maximum limits. This validation confirms the value is within the expected range before the calculation continues. When a value falls outside its allowed range, a warning is recorded for that input. This helps flag invalid data before it is used in calculations. The function returns a list of validation messages, including warnings or errors. It adds messages when required inputs are missing or when values fall outside their allowed ranges. This feedback helps confirm that all inputs are present and valid before any further calculations are performed. The function calculates cooling duty in kilowatts by first finding mass flow rate from the liquid flow rate and density. It then determines the temperature drop from inlet to outlet and uses these values to compute the heat removed per minute. Finally, it converts that result to kilowatts by dividing by 60. The cooling duty is found by multiplying the mass flow rate, heat capacity, and the inlet to outlet temperature difference, giving an energy transfer rate in kilojoules per minute. Dividing by 60 converts this value to kilowatts, because 1 kilowatt equals 1 kilojoule per second. Before running engineering calculations, the code checks whether the design case has all required inputs. The validation function returns any input issues it finds. If no issues are returned, the case is marked valid. Otherwise, it is marked invalid. This prevents calculations from proceeding with incomplete or incorrect data. The process first announces that it is checking the input requirements for the cooling duty project. It then reports how many inputs are required and how many have actually been provided. Comparing these counts helps identify missing information before the calculations continue. First, the program checks whether the input validation passed. If the inputs are acceptable, it uses the cooling duty function with the design case to estimate the cooling duty in kilowatts, then reports the result rounded to 1 decimal place. If validation fails, it asks for a review and shows up to 3 messages explaining the input issues. This script validates the inputs needed to estimate cooling duty in a chemical process. It checks that each required value is present, uses the expected units, and falls within an acceptable range. If the inputs are valid, it calculates cooling duty in kilowatts using mass flow, temperature change, and heat capacity. If validation fails, it reports the missing or out-of-range inputs instead of producing the estimate. Output planning. Output planning helps turn engineering calculations into useful conclusions. In chemical engineering scripts, results should show whether a design is acceptable, highlight key assumptions, and flag important values such as flow rates, pressure drops, or feasibility warnings. Planning outputs early prevents unclear data dumps and makes the results support real engineering decisions. Plan outputs around the audience and purpose. Engineers need concise summaries with labeled values and clear pass or fail results. Students may need intermediate steps to check their work. And workflow scripts should store results in structured files for comparison. Whether reporting distillation data or wastewater treatment performance, the goal is to turn calculations into a clear, useful engineering record. When designing script output, make uncertainty and unusual results clear to the user. Chemical engineering calculations often depend on assumptions and correlations, so the script should warn when results may be unreliable, such as when flow conditions fall outside a correlation's valid range or reactor sizing gives unrealistic values. Clear warnings and summaries help make the script useful for decisions and troubleshooting. Python code. Output planning. Before coding engineering automation, plan what the outputs should include. Use clear labels, units, and decision points, and save concise results so they can be reviewed easily. We import the CSV module to work with CSV files, a common format for tabular data. We also import path from pathlib to manage file locations more easily across different operating systems. A dictionary is created to organize the key inputs for a wastewater polishing reactor case. It stores the case description, daily flow of 1,200 cubic meters, inlet concentration of 85 milligrams per liter, target outlet concentration of 20 milligrams per liter, and a reaction rate constant of 0.18 per hour. These values provide the inputs needed for later calculations in the script. To size the reactor, first find the required removal fraction by comparing the target concentration with the inlet concentration. Then divide that fraction by the rate constant to get the needed residence time in hours. Finally, convert the flow rate from cubic meters per day to cubic meters per hour by dividing by 24. To size the reactor, multiply the flow rate by the residence time to find the required volume. Then calculate the outlet concentration by applying the remaining fraction after removal to the inlet concentration. The reactor meets discharge requirements if this outlet concentration is less than or equal to the target concentration. The summary dictionary organizes the main engineering results for review. It records the case name, daily flow rate, required removal percentage, residence time, reactor volume, and actual outlet concentration. It also checks whether the outlet concentration is at or below the target, giving a concise measure of whether the design meets the treatment goal. The process saves the summary results to a CSV file. It creates an output file path, opens the file safely in write mode, and uses a CSV dictionary writer with the summary keys as column headers. It then writes the headers and adds the summary values as one row, producing a structured file for later review or analysis. The output plan prints a concise summary of the treatment scenario, starting with the case name. It reports the flow rate, required removal percentage, residence time, reactor volume, and outlet concentration using clear numeric formatting. It then indicates whether the outlet concentration meets the discharge target and confirms the name of the saved results file. This script estimates the key design needs for a wastewater polishing reactor using the flow rate, inlet and target concentrations, and a rate constant. It calculates the required removal, residence time, reactor volume, and expected outlet concentration, then checks whether the discharge target is met. The results are summarized, saved to a CSV file, and printed with a brief confirmation. Integrated workflow. Function workflow. Treat each function in a chemical engineering script as a focused engineering task, such as unit conversion, property estimation, or material balance calculation. Separating these tasks makes the script easier to read and follow, because it reflects a clear sequence of engineering actions. Each function should make it obvious what information it receives, what operation it performs, and what result it returns. Functions become most useful when combined with organized data and loops. Data such as stream information or equipment settings can be stored in collections, then passed into functions as a loop repeats calculations for different conditions. This avoids rewriting the same logic for each case and makes the script easier to extend by adding new data rather than changing the core workflow. A well-structured function workflow turns calculated results into useful file outputs for review and future comparison. After functions produce clean data or engineering decisions, the workflow organizes the results so they can be saved or shared. In applied projects, this connects inputs, repeated analysis, and final deliverables into one reliable process. Python code, function workflow. Create one complete Capstone workflow using functions to keep calculations clear and readable. Save the results so they can be reviewed later. The code imports the CSV module to read and write structured CSV data. It also imports path from the pathlib module, which makes file path operations like creating, reading, and writing files easier to manage. The workflow begins by organizing 3 heat exchanger scenarios into a single collection of case data. Each case stores the flow rate, specific heat capacity, inlet temperature, and outlet temperature needed for later calculations. Case A, B, and C use different flow rates and temperature ranges, with case C also using a different specific heat capacity. This structure makes the scenario data easy to manage and compare during analysis. This function finds a stream's heat duty in kilowatts. It first calculates the temperature change from inlet to outlet, then multiplies that change by the mass flow rate and specific heat capacity. The result is the heat duty returned by the function. This heat duty classification function compares a calculated heat duty with a target value. If the calculated value meets or exceeds the target, the case is marked as meeting the target. Otherwise, it is marked as below target. This provides a simple way to judge whether each engineering case satisfies the required performance. The build result row function prepares stream data for saving. It calculates the stream's heat duty in kilowatts, compares it with the target value to classify the case, and returns a structured record with the case identifier, rounded duty, and status. Set the target heat duty to 150 kilowatts so each heat exchanger case can be judged against the required performance. Then prepare an empty results collection to store each case's calculated heat duty and classification. The process loops through each stream case and uses a result row builder to calculate its heat duty against the target. For each case, it records the case identifier, the rounded heat duty, and whether the target is met. These records are added to a results list, creating a compact table of outcomes for all cases. First, the workflow checks that the number of results matches the number of cases, confirming that each case produced exactly one result. If the counts differ, it raises an error because the processing did not complete as expected. This validation helps protect the integrity of the data pipeline. The setup creates a CSV output file for the heat exchanger summary using a cross-platform path handling tool. It also defines the column headers for the file, the case, the duty in kilowatts, and the status. These fields organize each heat exchanger result into a clear, readable row. The program opens the output file for writing, clearing any existing content, then uses the CSV dictionary writer to save results in a structured table. The column names define the order of the data. The header row is written first, and then each result dictionary is added as a separate row. This creates a clean CSV file that is easy to review and share. The code prints a short summary of the engineering workflow. It confirms how many cases were processed and reports the target heat duty in kilowatts, giving the benchmark used to judge each case. The program reviews each heat exchanger result and pulls out the case name, heat duty in kilowatts, and whether it meets the target. It then prints these values in a compact summary, making it easy to compare each case against the required heat duty. The code displays a confirmation message after saving the report. It includes the output file name so the user knows the data was written to the intended CSV location. The script evaluates multiple heat exchanger cases by calculating heat duty from flow rate, specific heat capacity, and temperature change. It compares each result with a target of 150 kilowatts and labels the case as meeting or falling below the target. It then saves the complete summary to a CSV report and prints the number of cases processed, each duty result, its status, and a confirmation that the report was saved. Loop logic. Loop logic lets a workflow repeat the same operation across many cases without rewriting instructions. In chemical engineering, this supports automation by applying calculations to streams, data rows, simulation points, or study conditions. Each loop pass handles one item, updates the results, and prepares the next step, turning a single calculation into a controlled sequence of repeated actions. Effective loop logic starts with choosing the right data structure for the task, such as data for temperatures, equipment settings, or lab samples. The loop should match the engineering purpose, whether evaluating designs or checking reactor data for deviations. This makes looping more than repetition. It applies consistent reasoning to data in a clear and efficient way. Clear loop logic makes scripts easier to test, update, and understand. Each loop should have one main responsibility, such as moving through data or producing results, while functions handle specific tasks. This separation keeps workflows organized and makes reused or modified scripts safer and more predictable in professional settings. Python code, loop logic. Loop logic manages repeated engineering calculations, while functions keep each calculation clear and easy to test. The results are collected before being written to a file. The script starts by importing tools for file handling. The CSV module supports reading and writing structured CSV data, while Path from Pathlib makes working with file paths easier and more platform independent. Together, these imports prepare the script for later file input and output operations. The content defines a collection of heat exchanger designs, with each design described by its name, surface area, heat transfer coefficient, and temperature difference. These values provide the information needed to calculate each exchanger's heat duty and compare its thermal performance. Organizing the data this way makes it easy to process and classify each design. This heat duty function estimates a heat exchanger's duty in kilowatts using the exchanger area, overall heat transfer coefficient, and temperature difference. It multiplies these inputs to get heat duty in watts, then divides by 1,000 to convert the result to kilowatts, a more practical unit for engineering calculations. The classify design function compares a design's heat duty with its target value. If the heat duty is at least as large as the target, it labels the design as meeting the target. Otherwise, it labels the design as below target. A target heat duty of 200 kilowatts is set as the benchmark for evaluating each heat exchanger design. An empty results list is then prepared to store each design's name, calculated heat duty, and whether it meets the target, making the evaluations easy to collect and review later. For each design, the heat duty is calculated in kilowatts using the heat duty function. This calculation uses the design area, heat transfer coefficient, and temperature difference, then stores the result as the heat duty for that design. The code classifies the current design by checking whether its heat duty meets the target. It then records the design name, rounded heat duty in kilowatts, and status in a result entry, which is saved for later use. The process sets a CSV output location using a cross-platform path tool, then opens the file for writing with proper new line handling. A context manager ensures the file closes correctly when writing is finished. The CSV columns are defined as name, duty in kilowatts, and status. And a dictionary-based CSV writer is created to map each record's keys to those column headers. The CSV writer first adds a header row to label the columns, then writes the result rows. Each row records a design name, its calculated heat duty in kilowatts, and whether it meets the target, creating a structured file for later review and analysis. To summarize the loop results, count how many designs meet the target by checking each result's status and totaling the matches. Then identify the best design by selecting the result with the highest heat duty in kilowatts. This gives both the number of successful designs and the top performer for heat transfer. The code reports how many heat exchanger designs were evaluated and how many met the target. It then identifies the best design by its highest heat duty in kilowatts. Finally, it confirms that the results were saved to a CSV file and gives the file name. The script evaluates multiple heat exchanger designs by calculating each design's heat duty from its area, heat transfer coefficient, and temperature difference. It checks whether each design meets the 200 kilowatt target, saves the design name, duty, and status to a CSV summary, and reports how many designs were processed and approved. It also identifies the best design as the one with the highest heat duty. Function workflow. A well-designed function workflow turns a script into a clear engineering tool. In chemical engineering, this means separating major tasks such as reading data, cleaning measurements, calculating balances, and preparing outputs into connected functions. This structure mirrors the engineering process and helps organize technical reasoning for better judgment. A function-based workflow works well when data structures carry information between stages of a script. Tables or dictionaries can store process data, such as temperatures and flow rates, while functions organize, analyze, and update that data for later steps. For example, separate functions might group heat exchanger trials, calculate efficiency, and compare results with expectations. This keeps the script clearer, reduces repetition, and lets the same analysis handle different conditions. A complete function workflow helps automate repeated calculations and file output using reusable, reliable building blocks. Loops can call the same function with different datasets, such as feed streams or reactor conditions, so results can be organized, saved, and reviewed. This makes engineering work more traceable and supports clearer reporting and decision-making. Python code function workflow. This example builds a complete function workflow for safely analyzing small reactor trial data and saving concise engineering results to a file. The script starts by importing tools for data input and output. The CSV module supports reading and writing structured CSV files, while the path class from pathlib provides a cleaner way to work with file locations and check or create files and folders. Together, these imports prepare the script to manage data files effectively. A trials list is created to store data for each trial in a structured way. Each entry records the trial identifier, the feed rate in moles per hour, and the product rate in moles per hour. This organization makes the measurements easy to access and use in later calculations. The function first identifies the required fields that every trial must include, such as the trial label, feed flow rate, and product flow rate. It then checks the trial data and records any required fields that are missing. This validation step ensures the trial has the necessary information before any further calculations are performed. The code first verifies that all required trial data is present and raises an error if anything is missing. It then converts the feed and product flow values to floating point numbers so they are ready for later numerical calculations. The function validates the flow rates before using them. It raises an error if the feed rate is 0 or negative, or if the product rate is negative, because those values are not physically meaningful. If the rates are valid, it returns them for later calculations. The function first validates the trial data to confirm required fields are present and the values are physically meaningful. It then uses the returned feed and product flow rates to find the converted amount by subtracting product flow from feed flow. This result represents the material converted during the reactor trial. The code finds the conversion rate by comparing the amount converted with the feed rate, showing what fraction of the feed became product. It then stores the trial identifier, feed and product flow rates, and the conversion expressed as a percentage. The function pulls the conversion percentage from each result, then averages those values. This gives one overall measure of conversion efficiency across all trials. The code finds the most successful trial by selecting the result with the highest conversion percentage. It then returns that best trial together with the average conversion, giving a compact summary of top performance and overall results. The function first sets the CSV field names by using the keys from the first result dictionary. This makes the CSV columns match the structure of the data, so the results can be written consistently and accurately. To save processed data as a CSV file, open the output file for writing with proper new line handling. Then create a dictionary-based CSV writer using the keys from the first result as the column names. Write the header row first, then write each result dictionary as a row, producing a CSV file that matches the data structure. An empty results list is created to collect conversion data from all trials. Each trial is processed with the calculate conversion function, which returns its conversion results as a dictionary. These dictionaries are added to the list, creating a complete collection ready for analysis or output. The reactor trial results are summarized by calculating the average conversion percentage and finding the trial with the highest conversion. The summarize results function produces these key values from the results list. The data is then saved to a CSV file using a path object for reliable file handling across operating systems. And the write results function stores the results in a structured format for review and sharing. The code finishes by reporting how many trials were processed, then summarizes performance with the average conversion percentage rounded to 1 decimal place. It also identifies the best trial and its rounded conversion percentage. Finally, it tells the user which file contains the saved results. This script analyzes small reactor trial data to calculate conversion rates. It first checks that each trial has valid, complete values, then compares feed flow to product flow to determine the conversion percentage. It summarizes the results by reporting the number of trials processed, the average conversion, and the trial with the highest conversion. The script also saves the summary to a CSV file and confirms that the output was created. Code review. Testing correctness. Code review. Testing correctness. A program is not correct just because it runs without errors. Its results must be checked for accuracy, proper units, valid data, and appropriate calculations for the engineering problem. In chemical engineering, compare outputs with known results or simple test cases to confirm the script can be trusted as a reliable tool. To check a program's correctness, use well-chosen tests that cover normal cases, boundary cases, and unusual inputs. For engineering scripts, this might include zero or extreme values, missing data, unexpected units, or predictable conditions such as no temperature difference. The program should handle bad inputs clearly, because automation errors can be costly. Correctness testing is a professional responsibility, not just a final step. To check correctness, follow the workflow from input to output and confirm that each step preserves the intended engineering logic. Make sure data is read properly, functions receive the right inputs, loops handle all items, and final results match the expected calculations. Use intermediate results to find where errors first appear, such as during cleaning or unit conversion, and confirm that the same input gives the same output unless randomness is expected. Python code. Testing correctness. Review tests help protect engineering automation by checking that decisions are correct. Small examples can expose hidden calculation errors, while expected answers make correctness clear and measurable. The code imports three useful tools: the CSV module for working with structured CSV data, the math module for accurate mathematical operations, and path from pathlib for clearer, object-oriented file path handling. This function calculates heat duty in kilowatts using flow rate, specific heat capacity, and temperature change. It checks that the flow rate is not negative and that the specific heat capacity is positive, raising an error if the inputs are invalid. When the inputs are valid, it multiplies the three values to return the heat duty. This calculation finds the heat duty in kilowatts by combining mass flow rate, specific heat capacity, and temperature change. The result represents the rate of energy transfer, which helps assess the thermal performance of the system. We define several test cases as organized records, each with a name, input values, and an expected heat duty. The inputs include flow rate, specific heat capacity, and temperature change. By comparing the calculated heat duty with the expected result, we can check that the calculation works correctly under different conditions. The process begins by creating an empty results list to record each test outcome. For every test case, it calculates heat duty using the heat duty function with the case's flow, specific heat capacity, and temperature change. The calculated value is then compared with the expected result using a very small relative tolerance to check precision. Each result records the case name, whether it passed, and the calculated value. This line adds a summary dictionary to the results list for one test case. It records the test name, the calculated heat duty in kilowatts, and whether the result matches the expected value closely enough to pass. This makes it easy to review each test outcome later. To test error handling, the heat duty calculation is called with a negative flow rate. The function should raise a value error because negative flow or non-positive heat capacity is invalid. If the error occurs, the test marks the bad input as handled correctly. If not, it marks the error handling as failed. The code sets up a CSV report file and opens it for writing with proper line formatting. A context manager ensures the file closes automatically, while a CSV dictionary writer is configured with columns for the case, the calculated kilowatts, and whether the check passed. It then writes the header row, preparing the file for the report data that will be added later. The writer object uses the write rows method to save all test results to a CSV file at once. Each row includes the test case name, the calculated heat duty in kilowatts, and whether the test passed, keeping the output organized and efficient. To evaluate the results, we count how many test cases passed and compare that total with the full set of tests. We also confirm that invalid input was handled by raising the expected error. Together, these checks show whether the function works correctly for both valid and invalid cases. The code reports how many correctness tests passed, whether bad input was handled properly, and whether the report file was written. It then gives an overall review result: pass when all tests succeed, and error handling works, or check when something needs attention. This provides a quick view of the code's reliability and readiness. This script verifies a heat duty calculation by testing expected results for typical operation, 0 temperature change, and 0 flow. It also confirms that invalid negative flow input triggers an error. The test outcomes are saved to a CSV file, and the script reports how many tests passed, whether error handling worked, and whether the overall engineering review was successful. Readability review. Readable code should let another engineer, or your future self, quickly understand what the script does and how it is organized. In chemical engineering work, clear structure and meaningful names help others trust, review, and maintain calculations such as reactor conversion or pump power estimates. A good script makes the problem, inputs, calculations, and results easy to identify without examining every line. Readable code clearly communicates intent. Comments should explain why decisions are made or what assumptions matter, rather than repeating what the code does. Use concise names that reflect the engineering meaning of the data, so teammates can understand and safely modify the script without unnecessary clutter. When reviewing code for readability, look for consistent formatting, clear naming, and structure that supports sound engineering judgment. Readable scripts make it easier to audit, reuse, validate, and make decisions without being distracted by unclear coding habits. Reviewers should also flag hidden assumptions, unexplained constants, and unclear outputs to improve transparency and reproducibility. Python code readability review. Use a small Capstone workflow to review readability and traceability in chemical calculations. The focus is on making the calculation structure clear, then scoring code review observations to evaluate how well the code supports that clarity. We import the CSV module to read and write structured tabular data, and use path from pathlib to handle file paths more easily across different operating systems. A list of review items is used to organize readability criteria for code evaluation. Each item records a criterion, a score, and a short note explaining the standard. In this example, clear flow is rated highly because the code moves logically from inputs to outputs, while meaningful names earns the top score because variables and functions use clear engineering terms. This structure makes code readability easier to assess and document consistently. The snippet adds readability review criteria for code. It rates useful comments based on whether assumptions are explained, consistent formatting based on matching spacing, and labeled outputs based on including units. Together, these criteria help evaluate code clarity and consistency. The function first gathers the score from each item into a list. It then checks whether that list is empty, and if so, returns an average score of 0 along with a message saying there are no items. This handles empty input safely and prevents errors when there is nothing to review. The function summarizes readability by calculating the average score, then comparing it with the passing score. If the average meets or exceeds the threshold, the review passes. Otherwise, it needs revision. It returns both the average and the final review status. The setup defines clear parameters for a review process. Each criterion can receive a maximum score of 5, and a review passes only if its average score is at least 4. It also sets a specific results file location using a path object, so the review output can be stored consistently. The code validates each review score to make sure it falls between 0 and 5. If any score is outside that range, it raises an error to indicate the scores are invalid. This helps keep the review data consistent and within expected limits. First, a readability summary is calculated from the review items and passing score, producing the average criteria score and a status showing whether the code passes or needs revision. Then, the lowest scoring item is identified to highlight the first area that should be improved. To save the review data, open the output file in write mode while avoiding extra blank lines. Define the CSV columns for the criterion, score, and note. Then create a CSV writer that uses those column names to write the data in a structured table. The code first writes a header row to the CSV file to define the columns for criterion, score, and note. It then writes each review item as a row, converting the dictionaries into a structured CSV format, so every criterion and its related information are recorded clearly. The output summarizes a Capstone automation readability review. It reports how many criteria were checked, shows the average score out of the maximum score, and states whether the code passes or needs revision. It also highlights the lowest scoring criterion as the first improvement target and confirms that the review file was written. This script reviews code readability using criteria like clear flow and meaningful names. It checks that scores are valid, calculates an average, and decides whether the code passes or needs revision. It then saves the results to a CSV file and prints a short console summary, including the first area that needs improvement. Engineering usefulness. When reviewing code for engineering usefulness, the main question is whether it helps engineers make decisions, work efficiently, or reduce errors in real situations. A program may run correctly, but still be unhelpful if it solves the wrong problem or gives unclear results. In chemical engineering, useful code should support practical tasks such as material balances or emissions tracking, use familiar inputs, check for missing data, and produce outputs that are easy to interpret and share. When reviewing code for engineering use, check that it can handle messy real-world data, including missing, incomplete, or noisy inputs. The code should flag unusual values, state its assumptions clearly, and separate raw data from conclusions. Its outputs should support practical decisions about issues such as safety and cost, without implying more precision than the data allows. Engineering usefulness means a script is easy to maintain, share, and understand after its first use. Good code uses clear structure and descriptive labels so others can adapt it without starting over. Reviewers should check whether it still works with larger datasets, changing conditions, or repeated analyses. The main goal is for the code to support reliable engineering decisions, not just produce numbers. Python code, engineering usefulness. Review code with a focus on engineering usefulness, making sure calculations clearly support plant decisions. Keep results concise, practical, and easy to act on. The script starts by importing tools for file handling and data input and output. The CSV module supports reading and writing tabular data, while the path class from pathlib makes file paths easier to manage across different operating systems. Together, these imports prepare the script to work with structured data files efficiently. The data is organized as a list of records where each record describes one day of small plant operation. Each record stores the day, monitored unit, flow in cubic meters, and inlet and outlet chemical oxygen demand values. This structure makes the plant data easy to access and use for later analysis. Set the minimum acceptable removal percentage at 70 to define the plant's performance threshold. Each record must also include the day, unit, flow in cubic meters, and chemical oxygen demand values entering and leaving the system, so the data is complete for calculation and assessment. The validate record function checks each plant record before calculations begin. It identifies any required fields that are missing or set to none, then verifies that the inlet chemical oxygen demand is greater than 0 and the outlet value is not negative. It returns the missing fields and whether the numeric values are valid, helping ensure only complete usable records are processed. The function estimates treatment removal efficiency by comparing inlet and outlet chemical oxygen demand, or COD. It subtracts the outlet COD from the inlet COD, divides by the inlet COD, and converts the result to a percentage. This shows how effectively the process reduces pollutants. To begin the engineering report, create two empty collections, one for processed summary results and one for validation warnings. The summary collection will capture key metrics such as removal efficiency and status, while the warnings collection will track missing or invalid data. Together, they organize the report outputs so the final result is clear, actionable, and easy to interpret. The process checks each record for missing required fields or invalid numeric values. Invalid records generate a warning with the day and problem, then are skipped. Valid records are used to calculate chemical oxygen demand removal efficiency, compare it with the required minimum, and assign a status of OK or investigate. Each valid result is then added to the summary with the day, unit, rounded efficiency, and status. The process creates a CSV summary file for wastewater review by setting the save location, opening the file for writing, and using a CSV writer to format the output. It first adds column headings for the day, unit, removal percent, and engineering status, then writes the process summary records. The result is a clean, shareable file that highlights key metrics supervisors can use for decision-making. The review output summarizes engineering usefulness by reporting how many records are usable out of the total, how many warnings need follow-up, and how many days fall below the target removal efficiency. It also identifies the saved summary file. The main purpose is to present results in a form that supports decisions, rather than only showing raw calculations. This script reviews daily wastewater treatment data to assess plant performance. It checks records for missing or invalid values, then calculates chemical oxygen demand removal efficiency for usable entries. Days meeting the 70% target are marked as acceptable, while lower results are flagged for investigation. It saves a CSV summary and reports the number of usable records, warnings, and days needing attention. In this lecture, you learn to design a complete Python script for an applied chemical engineering task, integrate functions, data structures, loops, and file output into one workflow, and evaluate project code for correctness, readability, and engineering usefulness. Congratulations on completing this course. Thank you for your attention. See you all in the next lecture.